Hello students, in this video we'll discuss the residue theorem, which is one of the most important theorems in complex analysis. What is the residue theorem? Well, we've developed all the tools to prove this theorem quickly, okay? The residue theorem says that suppose F maps a disk, I'll say D for disk, minus points P1, P2, Pn into C. So here D is just going to be a disk, right? So D is a disk, and the points P1 through Pn are isolated singularities. Okay, great. And F is holomorphic, right? Okay, so here's our situation. Our situation is the following. So you have a holomorphic function on a disk. Doesn't have to be a disk, right? I'm just doing it for simplicity, right? It could be a rectangular region, it could be a triangle, it can be a keyhole shape. There's lots of different things you can do, right? So in other words, it doesn't have to be a disk, but the most often times, or it can be half of a disk, right? It can be a keyhole contour, all sorts of, sometimes they refer to these things like toy shapes in some complex variables books. But doing things on a disk is a good first starting point, right? It generalizes very quickly to other regions which are homotopic to this boundary over here, right? And then there's going to be singularities over here, P1, P2, P3, Pn. Okay, there's all those singularities in there. And so what I claim is the following. So recall, then, I claim, the theorem states, then, if this is my circle C, right, then the integral over C of f of zeta d zeta is 2 pi I times the sum. J goes from 1 up to n, the residue of f at the point Pj, like that. Where what is residue, right? So a residue, so of course, what I know is I know that the function f near these isolated singular points, let me give an illustration of this. If I look at a point P2, for example, I can draw a circle around P2 that does not intersect any of the other singularities over here, right? I'm going to call that circle over here C tilde. And on that circle C tilde over there, I know that on the interior of C tilde minus that point P, I know that F has a Laurent expansion, right? So F near P2, right? I can write F near P2 is the following. We can say F of Z is going to be what? It's going to be the sum. N goes from negative infinity to infinity, some numbers a n, and then z minus p to the power n, right? And then a negative 1 over here is the residue, right? So I'm going to call that p, we can do for anything, pj, for example, right? So the residue of f at pj is just that number a negative 1 in this expansion, is the a negative 1 term in the expansion. It's the only one that integrates to anything, right? And so that's basically the whole idea of the residue theorem. Good. So how would you prove this thing over here, right? Well, it suffices to draw all these little keyhole contours and use the Cauchy theorem, right? So in other words, what you really want to do is you really want to start to draw all these keyhole contours, right? Like this, and then use the proof of the Cauchy integral formula, right? That would be the technical idea, but we've already done that, right? So I can say the following. So what we're going to do is, what's going to happen over here? So near any pj, so f of z is going to be equal to what? Near any pj can be written as an hj of z plus sj of z, right? Where hj is holomorphic, and sj, the singular part. I'm just writing down the Laurent expansion. I'm saying take the 0 to infinity terms, that's hj, take the negative 1 to negative infinity terms, those are the sj terms, right? So in particular, sj of z is really what? Is really some number, we'll call it like this, we'll call it a capital sub j negative 1 over z minus pj plus a negative 2j over z minus pj squared, right? And so let's examine what happens over here. So the integral over C of hj of z plus sj of z dz is going to be what? The hj is holomorphic, integrates to 0, right? Perfect, right? That's just by Cauchy. Okay. What does the Sj integrate to? So this is the integral over C, and I'm going to plug in this expansion. It's a negative 1j over z minus pj dz, and whoops, just kidding, etc., right? Plus a negative 2j over z minus pj squared, etc., 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 dz. Now, all the terms past 1 integrate to nothing, right? Because that's a calculation we already know how to do, right? So the only power, if you integrate a power around the circle, right, the only term that survives is the power that corresponds to negative 1, right? And that's this term over here. So all this integrates to is just what? Just 2 pi I times a negative 1j, which is, of course, is just 2 pi I times the residue of f at pj, right? And so now this is a local calculation, so what does that tell me? That tells me now that the integral f z dz is nothing more than what? I do this n times, I write down all of these n expressions over here, and I deduce that this is equal to what? It's equal to the 2 pi I times the sum, j goes from 1 to n, of the residue of f at pj, and that is the residue theorem, right? This is a very, very useful mechanism, right? It allows me to compute integrals extremely fast, right? I'm going to give you two really, so that's the residue theorem. Beautiful, right? And so what maybe will be, let's do a simple example of this, right? So it would be a simple example. Let's do one simple example. I'm going to do some calculations over here. So it's an example over here, okay? So the simple example is going to be, what's the integral over the unit circle of what? Of, let's do a simple guy over here. So let's just do 1 over sine. That's going to be the only root, so I want to do something different over here. Let me do something a little slightly different. Let's integrate over the circle, twice the unit circle, and then a dz over z squared plus 1, which is, of course, the integral over twice the unit circle of dz over z minus I, and then z plus I, right? Okay. And so this is going to be just 2 pi I times the residues, right? 2 pi I, the residue of this function. Let's call it a function over here. So let's call it g of z, z squared minus plus 1 to negative 1, right? It's the residue of g. The singularities are going to be I and negative I. At I plus 2 pi I, the residue of g at negative I, because both negative I and I are inside twice the unit circle over here, right? Of course, you can see that the residue at I is going to be just 1 over 2i. The residue at negative I over here is going to be negative 1 over 2i, right? So how did I do it so quickly? Let's do a little lemma that helps me improve this over here. So here's the first lemma. That's very useful for us. So if p of x, p of z over q of z, sorry, I'm researching a problem right now that involves p of x, right? So that's on my mind. P of z over q of z has a simple pole at, let's say, z equals p, z equals, z equals a, then the residue of p over q at the point A is going to be what? It's going to be p prime over q of a. Let's figure it out. Let's actually just do it, right? So if it has a simple pole, it means that q of a is equal to 0, right? So this is going to be, if I expand this out, p of z over q of z. If it has a simple pole, that means that p of a is not going to be equal to 0, right? But q of a is going to be equal to 0, right? So this is going to be p of a plus p prime of a z, etc. over what? Over q of a is going to be 0, so I'm going to have a q prime of a, z, etc. over here. And so if I just do the division, the only term over here when I do the division that's going to have a 1 over z is going to be a p of a over q prime of a. So this is going to be equal to p of a over q prime of a for a simple pole. Beautiful. And that's how I did the calculation so quickly over here, right? Because what's my function over here? So my function over here, my p, is going to be what? And then the q prime is just going to be what? The q prime for these functions is always going to be equal to 1, right? So for this function over here, the residue at this thing over here, this number over here is going to be what? That's going to be 2 pi I times what? The residue of g at I. Well, now my function over here, my q is really what? Is really a z minus I, and my p is really 1 over z plus I, right? So I'm just going to plug in 1 over z I into 1 over z plus I, and over here, what we're going to plug in, then the q prime is going to be equal to 1, right? So I'm going to plug in a 1 over 2 pi I 2i. Then over here, what's this integral going to be? This integral here is going to be the same thing, so the negative 2i, right? So this is going to be 2 pi I. That's going to be 2 pi I times what? Times negative 1 over 2i. Well, look, those are equal and opposite, so this integral over here just integrates to 0 by the residue theorem. Now, it usually doesn't happen, right? Usually the residues you start to accumulate. This is an example where there's perfect symmetry over here because they're perfectly aligned and antipodal against this symmetric function over here, right? That's the reason why it happens. In further videos, we'll really sort of take this residue theorem and apply to contours that are, like I alluded to, are homotopic to the circle, right? Whose regions are basically structurally, topologically equivalent to the disk. And then we'll use this to be able to compute a tremendous number of real integrals that go from either 0 to infinity or negative infinity to infinity, just by summing the residues, right? Ensuring that other contributions of those curves tend to 0 as the parameter in those expressions tends to 0. Very, very useful calculation device, and we'll do a ton of examples to really illustrate how effective the residue theorem is in computing real integrals. Thank you very much.